Hello everyone, you're welcome to this channel once again. Today we have another peculiar question from a propeller-driven airplane and how to calculate its power required during the flight. Once again, we have another question from a propeller-driven airplane and how to calculate the aircraft power required at low altitude. Now, let's read through the following question. Consider a propeller-driven aircraft with the following parameter. The wing area S equals 16 meters squared. The wingspan B equals 11 meters. The weight of the aircraft equals 9 kilonewton. The zero lift drag coefficient CDO equals 0.04. The Oswald efficiency factor E equals 0.78. Now, calculate the power required, PR, at low altitude, where the air density, rho, equals 1.2 kilogram per meter cube, and to perform a straight and unaccelerated climb at climb angle gamma equals 25 degrees, and the velocity of the flight equals 30 meters per second. Now, we are to ignore the aerodynamic power losses of the propeller and other inadequacies. Now, to approach this particular question, firstly, let's pull out the parameters. Today we have a propeller driven aircraft. We have the wing area, 16 meters square. We have the span of the wing, 11 meters. We have the weight given, 9 kilonewton, which is 9,000 Newton. We have the CDO, 0.04. We have the Oswald factor, 0.78. We're supposed to calculate the power required. We have the rho, 1.2 kilogram meter cube. We have the gamma, 25 degree. We have the flight velocity, 30 meters per second. Don't let us forget from these both values we can deduce our aspect ratio for the aircraft. Give us 7.56. Now, for us to approach this question accordingly, we need to draw the representation of the flight schematic. the weight is acting, the head of the aircraft is acting downward, while the drag, the thrust, and the lift. As a thrust, the lift, the drag, and the weight. Also, the subtended angle gamma, which is the climb angle. From the particular diagram, we can deduce that the lift equals W cos gamma. Likewise, we can deduce that thrust equals D, which is the section here plus the section over here. So that becomes W sine gamma. Now that we can deduce this equation from the flight schematic diagram, we also know that load equals half rho x v squared CL. So therefore CL equals 2L over rho x v infinity squared. So therefore our CL becomes 2 cos gamma W over rho s v infinity squared. So therefore our CL becomes 2 multiplied by the weight, 9,000 times cos 25 over what's the rho, 1.2 times 16 times the v infinity, which is 30 squared. So CL becomes 0.94441. Don't let us forget our CD equals CDO plus CL squared over pi EAR. So our CD becomes, what's the CDO? 0.04 plus our calculated CL 0.9441 square over 3.14 times, what's the Horsford factor? 0.78 times our aspect ratio, 7.56. So our CD equals 0.0881. Now that we have calculated that, we can deduce that if CD equals d over rho x v square, then the drag will be half rho s v infinity square CD so therefore the drag becomes half multiplied by the rho 1.2 multiplied by the wing area 16 times the v 30 square multiplied by the CD 0.0881. Our drag equals 761.17 Newton. From there we can deduce that T, which is a thrust, going with the calculation here, equals drag plus W sine gamma. Then we can deduce our T, which is a thrust, equals 761.17 plus 9,000 sine 25. Our thrust becomes 4,565 Newton. And we know that power required equals the product of the thrust to the flight velocity. So our power required equals 4,565 multiplied by 30. Our PR equals 136.95 kilowatt. So our PR, that is the power required for the whole flight, equals 136.95 kilowatts. Thank you for staying tuned.